before I finish the proof of, or sketch of the proof of Milnor's theorem, I want to emphasize something that maybe was not clear in the previous lessons. I discussed that yesterday with you, that what is the meaning for a map to be conformal? Why is it useful to have a conformal map? I mean, why people at the beginning of map making began looking at conformal maps, like, for example, Gauss. This is very simple, because if you have a big map, let's say a map of Brazil, for example, most of the times you do not care about respecting distances between faraway cities. I mean, if you have a mistake in the distance between Rio and Recife, that's not so much important. Usually when you open a map, you need it only locally. You need to understand what's happening in your neighborhood. And in your neighborhood, it's good to have a map which is just rescaling. So it's good to have a conformal map, because conformal map on the small scale is just a homotopy. So this is why people like Gauss were really interested in maps which locally are good for you. But on the large scale, it's good if the global shape is preserved, but it is not so fundamental. It is less important to preserve distances on the large than having a conformal map in the small. This is why conformal maps are useful. Okay? Okay, nevertheless, this question of Milnor is interesting. So let me finish the proof of Milnor's theorem. Milnor claimed and proved that if you take the sphere and if you take the polar cap of angle alpha, and if you look for a map phi in the plane, then the theorem is that the best map with respect to what I defined yesterday, the Lipschitz constant, the best map is just the inverse of exponential map. Okay, so the best, I would put it this way, any map, let's say phi, from the polar cap to the plane, which is Lipschitz, that is distance in the plane between phi x, phi y is less than k2 distance xy in the sphere and more than k1 distance of xy is such that k2 divided by k1 is at least alpha divided by sine alpha. Moreover, if k2 divided by k1 is equal to alpha sine alpha, then the map phi is just the inverse of the exponential map. Is the inverse of the exponential map. Remember, the exponential map goes from the tangent plane to the sphere. Okay, so let me prove that. You will see it is not hard. Okay, so I take a Lipschitz map from the polar cap to the plane, and I want to understand the image of the alpha. Of course, the image of the alpha is some domain in the plane. We can assume containing the origin. I can assume, for simplicity, that the North Pole is mapped to the origin in the plane. So I have, this is the image of my map. Now I just note that any point on the boundary of the polar cap is at distance alpha from the North Pole. Therefore, therefore the images of the 2 points, North Pole and X, are at a distance at least k1 alpha, which means that the boundary of this Jordan domain is at a distance at least k1 alpha from the origin. In other words, the circle of radius k1 alpha is completely contained in the image of the map. Okay? Now, what can we say about this Jordan curve, which is the boundary of this d alpha, phi of d alpha? Well, I claim that it is a Jordan curve going around the origin with index 1, just because the origin is inside the interior of the Jordan curve. Now, what do we know about the length of the boundary of phi of d alpha? What can I say about the length of phi of d alpha? Well, on one side, I can say I have a curve going around the disk of radius k1 alpha. So its perimeter, its length, is at least the perimeter of this disk. Is that clear? If you have a curve going around the disk, the length of the curve is at least the perimeter of the disk. Well, either you believe it or you go to Milnor's paper with a complete proof and very detailed for first-year students, very clear. Anyway, so the length is at least 2 pi k1 alpha. On the other hand, this curve is nothing more than the image of the boundary of d alpha by the map. The boundary has length 2 pi sine alpha, because the radius of this circle here is sine alpha. So under the map, since we have a Lipschitz constant k2, the perimeter, the length of phi of the alpha is less than or equal to k2 times 2 pi sine alpha. End of proof. This implies that k2 divided by k1 is at least alpha sine alpha. Okay? So that's very simple. Probably the simplest theorem of Milnor. Okay? Well, maybe we can find others, but this one is simple. Well, if you want to make the proof completely rigorous, well, you notice that I used some kind of argument which was kind of not completely clean. I said, well, the curve is going around with index 1, so I was using somehow the index of curves, and then I said a curve going around a disk must have perimeter, at least the length of the perimeter of the disk itself, which again is not completely clear. It has to be checked and proved correctly. So it's not so easy actually. Now let's look for the second part of the theorem. If we have k2 divided by k1 is equal to alpha divided by sine alpha, we want to prove that this is indeed the exponential map. Well, so we have to look at these inequalities and see what's happening when there are equalities. So what's happening if this is equality? Well, you see, if you have a curve going around a disk whose length is exactly equal to the perimeter of the disk, there is no much choice. This curve has to be equal to the boundary of the disk. Again, you have to prove it, but we can believe that, okay? So you see that if we assume that k2 divided by k1 is equal to alpha sine alpha, it follows that the image of the disk is precisely the circle. Not only that, but since we have a Lipschitz map with constant K2, on the boundary, it has to be an isometry of the circle. In other words, the phi restricted to the boundary of d alpha is just sending the circle to the circle respecting angles. Okay? Is a rotation. What I mean by that is that 2 points on the boundary with a certain angle are mapped by the map on 2 points on the boundary with the same angle. So at least this means that the map restricted to the boundary coincides with the inverse of exponential map on the boundary. Now I just have to see what's happening inside the disk. And that's very easy. Look. So let me draw a picture again. This is the polar cap. This is the North Pole mapped to a disk. What I know is that on the boundary of the disk polar cap, everything is like rotation. Now I pick a point which is neither the North Pole nor on the boundary. I want to determine its image. Well, I take the meridian like that. This gives me a point. The North Pole, I know where it goes, here. This point x, let's say it goes here, phi of x. And this point P, I want to determine where it goes. And I want to say it goes there. So, to a point with the same distance to the North Pole. So where can it go? Well, at least let me call this distance here alpha, not alpha, delta, and this distance here is alpha minus delta. So this point P is a distance delta from n, and distance alpha minus delta from x. So the point should be mapped to a point here, which is a distance at least k1 delta from the origin, and at least k1 alpha minus delta from this point. So this places the image of the point P outside of two disks like that. The image of the point P has to be a distance at least k1 delta from the origin and k1 alpha minus delta from this point phi of x. So the image of point P is somewhere outside of these two disks. Now I claim it has to be exactly here. Why? Look. Look, for example, at these 2 points. They come from 2 points here. But I know on the boundary the map is a rigid motion. So these 2 points are mapped. These 2 points here are mapped to these 2 points here. Now the point P, it has a certain distance from these 2 points, and by the map, the distance are multiplied at least by k1. So the image of P has to be outside this disk and outside this disk. No much room left, it has to be here. So that's an easy exercise to show that under the condition of equality between k2 divided by k1 and alpha sine alpha, the map is restricted to be the exponential map, or more precisely, the inverse of exponential map. Again, for more details, you have a look at the paper of Milner. I was explaining that to Marco, that I checked yesterday in Mathematical Reviews papers of Milner. He's such a famous mathematician. He wrote so many wonderful papers with so many citations, and this paper has the least number of citations among all papers of Milner. Has been cited twice, only twice. So, I think I don't understand why, because I think this question about knowing if the best map is a diffeomorphism is a real nice mathematical question. And the fact that the paper has been cited only twice, means that maybe nobody tried to prove it. So maybe it's a good problem for you. Okay, so let me stop with non-conformal maps. And let me begin some other chapter. I will begin discussing Riemann theorem. So Riemann theorem which says that, again in quotes, that a simply connected domain let's say U in C different from C is conformally equivalent to the unit disk. So you're given some domain in the plane, U, you assume it's simply connected, and the goal is to find a holomorphic map, conformal map, to the unit disk. Well, let me make first a few comments. First of all, Riemann never stated the theorem this way. Riemann was making an extra assumption. He was assuming that the boundary of U is a smooth Jordan curve. Of course, again, I'm making some historical mixtures because Jordan was born but was not active. He was a little kid or something at the time. But he was assuming that the boundary was nice. And the second comment I'm going to make, I will explain that better, is that the proof that Riemann is proposing is not correct. So I want to discuss, first of all, this non-correct proof, and then I will try to discuss how people reacted with this non-correct proof. So this proof of Riemann is based on what Riemann himself called the Dirichlet principle. So this is in Riemann's terminology, in Riemann's thesis in 1851. So the Dirichlet principle allows you to prove the following theorem. Any continuous function let's say, f from the boundary of such a domain, of a Jordan domain, to the real number, can be extended uniquely to a harmonic function. So I will explain to you how this theorem, let's say theorem B, implies theorem A. This is correct. This is contained in Riemann's thesis. And then I will, or maybe before, I will try to explain to you what is the proposed solution of theorem B by Riemann. And you will see that this proposed solution is not correct. So what is true, and the proof of Riemann, everything is true here. But the fact that B implies A is indeed correct. This is indeed in Riemann's thesis. Theorem B is correct, but the proof given by Riemann is not convincing. And I will discuss that now. First example is what's happening when the domain is a disk. So let's begin by the simplest case. In the case of the disk, you are given a function f on the boundary of the unit disk, and you want to extend it holomorphically, harmonically. To the disk. This is the simplest special case of theorem B. What is amazing is that I'm going to tell you that it's easy to do. And what is amazing is that obviously Riemann was not aware of this solution. Today we call that the Poisson formula. I will explain that to you immediately. The story and the history of this Poisson formula is very unclear. We looked at that rather carefully. One, it is clear that Riemann was not aware at all of Poisson formula. Schwarz, in 1870, finds this Poisson formula and claims that he is the author of Poisson formula. According to Dieudonné thinks that this Poisson formula is due to Green in 1828. So again, Dirichlet principle 1851, so Riemann could have known Poisson formula. Schwarz in 1870 claims that he created it. And Poisson had a formula in the 20s, but we found that in Dieudonné. Dieudonné says that one can find a form of Poisson formula in the papers of Poisson, but it does not give more precision. So I don't know. We couldn't find it. And as late as 1871, Prim, the famous algebraic geometer, Prim, was totally unaware of Poisson formula. He writes some silly comments about extending harmonic functions on the disk, on the circle to the disk. So really, it took a long time before this standard Poisson formula that we teach in elementary courses in complex analysis became standard. I mean, people as famous as all these guys did not know Poisson formula. So let me try to explain this Poisson formula in the simplest possible way. Okay, so here's a possibility. There are several ways of explaining it, but here's a possibility. Suppose you take the upper half space, so H, so the complex numbers W with imaginary parts of W positive, and you consider the function on H mapping W to imaginary part of W. Since this is the imaginary part of the holomorphic function, the function W, it's a harmonic function. And of course, this harmonic function, when you restrict it to the boundary, is 0. So you have already some kind of feeling that this is counterexample to the uniqueness of the harmonic extension, because the function 0 on the boundary can be extended in many ways as harmonic function. It could be extended by 0, it could be extended by imaginary part of W. So what you can, of course, it's not a counterexample. If you want to produce that to the disk, you have to map W to Z, Z being W minus I, W plus I. You see, if you take a point here, I, any point W in the upper half space is closer to I than to minus I. So W minus I has a modulus less than W plus I, which means that the Z is indeed in the unit disk. And this is the famous transformation, transforming the upper half space to the disk. So what we can do now is to take this function W, which is a harmonic function in the upper half space, and look at this function as a function of Z. And what you get is a function of Z, which is still harmonic, of course, and we can explicitly compute it. It is the function f of Z equal to, that's easy to do. You take a Z, compute W, take imaginary part, and the result is f of Z is 1 minus modulus of Z squared, 1 minus Z squared. So you see, this is a harmonic function in the disk whose value on the boundary is 0. But it's not counterexample to the assertion, of course, because on the boundary, it is not continuous. It has a singular point at Z is equal to 1. So it's better to think of this harmonic function in the disk as having on the boundary a value which is 0 everywhere except at 1 where it is a Dirac mass. So if you want to construct a harmonic function with a given value on the boundary, the idea is just to average this special function having as the boundary the Dirac mass 1 over the circle. So what you do is this, and then you can check it immediately. If I want to produce a Dirac mass at the point exponential of A theta, it's just enough to replace this. This is a harmonic function in the disk whose boundary value is a Dirac mass at exponential E theta. So you have the following Poisson formula. Which says the following: you are given a function f on the unit circle, and you define f bar of Z on the unit disk just by taking the average of that on the circle. So you define this. And here you put 1 minus z minus z squared, and here you put exponential. Here it is. And since this quantity here is just an average of harmonic functions, it's a harmonic function. So this gives a formula which f bar is defined now on the disk, is harmonic, and its boundary value restricts to f. So this is a very simple way to extend any continuous function to a harmonic function in the disk with no analytic problem. Okay? So again, this, I have no idea who understood that first. And it is amazing that Riemann did not know it. So what is the strategy for Riemann to solve his Dirichlet problem? No comment about that. They knew absolutely, no. First, even in the case of Riemann, when I said smooth, in his case, it's actually piecewise analytic. But he makes absolutely no comment about regularity on the boundary. No comment. It's well, this formula, the continuity of the extension is harmonic. The extension is harmonic in the disk. What is your problem? You want? Yes, it is. Yes, it is. I'm not sure, but I know it, and you know it. I mean, proving continuity of this on the boundary is very easy. Okay. That's easy. Yes, with the formula. Yes. Okay, so now let me go to the way Riemann was thinking about solving this Dirichlet problem. So Riemann says, okay, I'm given some domain U. I'm given a function f on the boundary, which is supposed to be a smooth curve. And Riemann says, let me consider for each possible extension, let's say f bar, any extension of f to the disk, smooth extension, he considers the integral over the disk of the energy called that the energy of f. And the idea of Riemann is, let us take a function f bar which minimizes this energy. So you minimize this energy. Over all possible extensions of f. And Riemann claims that this minimum occurs precisely for the unique harmonic extension of F. Okay, so this is the claim of Riemann. Claim there is a unique minimum for this energy functional. And this minimum is the unique harmonic extension. So for us it's kind of shocking because we are used to the fact that if you have a functional acting on some infinite dimensional space, we know that there should be no reason to have a minimum for this functional. And I think Riemann surely knew it, but anyway, he does not give any idea why there should be a minimum. So he says, this is, first, there's an interesting comment that for some reason the collected papers of Riemann were translated in French a long time ago, but to the best of my knowledge, they have never been translated in English for some unknown reason. You know, one of the most important mathematicians, no translation in English. Anyway, so in French, he says, let me translate in English, he says that since this functional takes a finite value for each f bar and goes to infinity when f bar goes to infinity, and since it's continuous, there is a minimum. So it's a mistake. Okay. So he makes this mistake, but he's right when he says that if there is a minimum, this minimum is indeed a harmonic function. So let me prove that, and that's very easy to do. If you assume it's minimum, if f bar is a minimum, let me show that indeed this implies that the Laplacian is 0, that is, the extension is indeed harmonic. How do you do? Well, you compute the energy of f bar plus a small perturbation, like epsilon h, where h is a function which is 0 on the boundary. So if you add some epsilon h on the boundary, to f bar, you do not change the value on the boundary. So if you compute that, since you see it's a quadratic form in f, well, you get e of f bar plus e plus epsilon square e of h plus 2 epsilon integral of, how is it, grad f bar grad h. So you see, if it's a minimum, that means that this quantity has to be 0 for every h. A polynomial of second degree, you want a minimum at 0, it should have no linear term. So you get from this, if you have a minimum, that the integral of gradient f bar gradient h is 0 for every h vanishing on the boundary. But this by integration by part, or by Green's formula, whatever, is equal to the gradient of f bar, of the Laplacian of f bar h, is equal to 0 for every h vanishing on the boundary. And the fact that this integral is vanishing implies indeed that the Laplacian f bar is 0. So Riemann was right when he said that the minimum of this functional, if it exists, is indeed a solution of the Dirichlet problem, but he was not right in saying that it was obvious that there is a minimum. And then Riemann was strongly criticized immediately, I mean, rather quickly. He was first of all criticized by Weierstrass. Weierstrass and Riemann were not really good friends. They had very different approaches of mathematics. You know, Weierstrass was making computations and Riemann making pictures. And Weierstrass gave a counterexample, not to that, but Weierstrass showed a very simple example of some functional in the same spirit as this energy functional, for which it is easy to see that there is no minimum. The example of Weierstrass is the following. You consider the set, let's say, of functions f from -1 + 1 to r, and you impose that at 0, at -1 takes the value -1, and at +1 it takes the value +1. So you look at the space of functions going from there to there. For every such function, you define the energy of f to be, by definition, the integral from -1 to +1 of x squared df dx squared. So, you know, it's kind of the same spirit as the energy that we defined before. You really take the integral of the norm of a gradient squared, except that you put here a weight, and the weight is x squared. It's a positive weight, and this positive weight vanishes at the origin. And that what Weierstrass does is that he says, look, I'm going to show you that there is no minimum for this functional. And just looks at the following functions. You take a function like that. It's a function which is almost 0, almost -1 here. And then very quickly here, and almost 1 here. Take a function fn, which is like that. It's a function which is almost... And then you compute this number for this function fn. And what's happening is that, of course, the derivative of fn is big, close to 0. But at the point where it is big, x is very small. So you do the computation, and this has been done on purpose, so that when you do the computation, this x squared is winning the game. And you compute, and you get this goes to 0. So indeed, you can find functions for which this energy is as small as you want. So the minimum is 0. But of course, if you look for a function for which this integral is 0, the only possibility is that dx d squared is 0. The only possibility would be a constant function, but the constant function is not in our space because it should go from -1 to +1. So it was terrible. Fortunately, Riemann was dead when when Weierstrass published that. But so he couldn't answer. Okay, so there was this strong criticism from Weierstrass concerning this proof. And there were other criticisms coming not from the enemies, but from the friends, in particular from Schwarz. Schwarz was a student.
But modern methods could show that there's a unique minimum, isn't that true?
Yeah, I'll go to that next class. Yeah, but you are right. I mean, Riemann was right, after all. I mean, Riemann was right. There is indeed a minimum for this for this functional, and this will be proved by Hilbert in 1900. Okay, so the correct proof of this existence of this minimum will be obtained by Hilbert in 1900. I hope to go to the proof of that next class. Okay, again using not modern. If you take a standard modern book on that, they will go to Sobolev spaces and Poincaré inequality and compactness arguments, etc., which is certainly correct and certainly beautiful. But all these arguments are using ideas much later than Hilbert. So what I try to do, I think tomorrow, will be to give you a proof of that, inaccessible to Riemann, but accessible to Hilbert, and by the beginning of the 20th century. But you're right. I mean, Riemann was right, after all. Like, for example, for the Riemann hypothesis, I don't know, he was right. You know? Okay, so I wanted to say that Schwarz, be careful, don't put a T here. Schwarz is Hermann Schwarz, Laurent Schwarz is Laurent Schwarz. Laurent Schwarz has a T, and Hermann Schwarz has no T. Okay? So many people make mistakes, it makes me upset with that. Anyway, so Schwarz was a good student of Riemann. He was really admiring Riemann. But what happened is that he couldn't believe this proof. And in particular, he couldn't believe, he did believe what I'm going to explain to you now, that theorem B implies theorem A. So he did believe this implication, but since he couldn't believe the proof of theorem B, he couldn't believe the proof of theorem A. So he said, after, it's written somewhere, after a seminar, he complained that even in the simplest cases, the Riemann mapping a simply connected domain to the disk, he complained that he could not understand that and he couldn't believe that. So he said, let's begin by the simplest possible example. And he said, let me try to understand the case where the domain U is a triangle. So this is really the motivation of Schwarz, was to prove the theorem of his master in a very simple case. So he wanted to prove in the case of a triangle, and he did prove it. He found the conformal mapping from the interior of a triangle to the disk. This is called the Schwarz mapping. I will explain that to you. But again, you have to keep in mind that the idea is not to use Riemann to find the uniformization of Schwarz. Riemann was really testing if Schwarz was right or not. And then Schwarz said, okay, now I did it for the triangle, maybe I can do it for a polygon. And then, I will explain that to you probably next time, Schwarz could not do it. What Schwarz did is that he found the general form of what should be such a map, but he could not prove that there is a map from the polygon to the disk directly. I will explain that to you why there are some difficulties, why the case of the polygon with more than 3 sides is much more complicated than the triangle. He could not do it. So he had to create new ideas by taking approximations. And what finally he did is that Schwarz, using some method I really want to explain to you next time, which is called the Schwarz alternating method. Schwarz showed that if you have two domains, simply connected domains, U1 and U2, if the intersection of the two is simply connected, if you know how to find a conformal map from U1 to the disk, if you know how to find a conformal map from U2 to the disk, he is able to construct a conformal map from the union of the two to the disk. By a limiting procedure. So if you start with two domains for which you know it's true, by this procedure I will describe tomorrow, he is able to construct the conformal map for the union of the two. And this construction is by some kind of limiting procedure. You will see that.
Is there any hypothesis on the intersection?
Simply connected. Okay. So he was happy because since he could do it for triangle, then you can glue triangles like that. You know, with several triangles, you can make more pictures. And if you glue together triangles, you get all polygons. So he was happy because then he could solve his problem of finding the conformal mapping from the polygon to the disk. And finally, by some kind of limiting argument, not completely clean, he could finally prove the theorem of his master. But the strategy was really different. Again, you start with a triangle for which he has some kind of very explicit mapping. Then there is this procedure of alternating procedure to glue, so to speak, two conformal mappings from two domains to make them somehow coincide on the intersection and construct a global mapping of the union. And then by some limiting procedure, you had the conformal mapping for any polygon, and then for any simply connected domain. Moreover, Schwarz showed something else, but the same idea. He showed the following. Suppose you have a surface and on this surface you have two domains which are simply connected, like this one, U1, and this one, U2. So U1 and U2 are simply connected, and you assume that you know that U1 is conformally equivalent to the disk, and you know that U2 is conformally equivalent to the disk. And you assume that the intersection of the two domains is some annulus. Then Schwarz shows that then you can somehow, using the same kind of idea of alternating procedure, you can prove that the union of the two, in other words, the full surface, is conformally equivalent to the sphere, to the round sphere. Then you can find a map which is conformal to the sphere. So you see, after all this, Schwarz had a proof of the global Gauss theorem. I remind you that yesterday I discussed Gauss theorem. You have a surface, you have a small country on the surface, you can map it conformally to the plane. Now this theorem is much, much better. It tells you that if you have a surface, any surface, simply connected surface, it's possible to map it conformally, globally, to the plane. So let me state it this way. This is the theorem of Schwarz. Theorem. Any Riemannian metric on the sphere is globally, conformally equivalent to the round sphere. So you see, this is a global version of the theorem of Gauss. Not only you can map a small country to the Euclidean plane, but you can globally, the surface can be mapped conformally to the sphere. If you want to express it in a more sophisticated way, you could say on the sphere S2 there is a unique complex structure. Up to by holomorphism. Any complex structure on the sphere is, any two are isomorphic. So this is the first example in history of a global uniformization theorem. You are given a structure like global surface, and globally you map it to a standard object, in this case the round sphere. Okay, so this is totally independent from Riemann. I mean, these theorems of Schwarz are not using theorem A or B, because again, Schwarz was suspicious about this theorem. Okay. Now I want to take time to prove that theorem B does imply theorem A, which is indeed what Riemann did. And so tomorrow I'll go to this wonderful story of Schwarz and triangles and polygons and alternating, and this is a very beautiful construction. Okay, so I remind you that we assume B, that is, we assume that given a function on the boundary of some domain, it can be extended by some harmonic function. And from this, I want to prove the theorem according to which any simply connected domain, U, can be mapped to the disk by some conformal map. So the idea is, today we have many proofs of that. the standard one that one finds in textbooks in complex analysis uses Montel families. Take compactness of the... But Montel theorem, compactness theorem of Montel was proved in 1912. So it was totally non-accessible neither to Riemann, neither to Schwarz, and even not to Hilbert. This kind of compactness argument, the idea that one can define, understand compact subsets in infinite dimensional functional spaces is much, much later. It's typically an idea of the 20th century. So the idea is this. Suppose you take, let's say, a point here. Let's say Z0 inside. I want to map it to the disk. Say I want that phi of Z0 is the origin. Then the idea is that instead of looking for this holomorphic function phi, we look for the log of phi of z. So, of course, as you know, the log of a complex number is not well defined. It's defined up to multiple of 2i pi. So what is well defined is the real part of that. It's the real part of a holomorphic function, so it's a harmonic function. So the question is, how can we construct at least the real part of the function phi you are looking for? And what can we say about this harmonic function u? Well, we know its value on the boundary. Because if z is in the boundary of u, what we know, we want that phi of z is of modulus 1. So the log of phi of z will be the log of a complex number of modulus 1. So it will be purely imaginary. So the real part is 0. So on the boundary should be 0. So it's a harmonic function which is 0 on the boundary. But of course, the trick is that this function phi has a 0 at z0. Phi of z0 is 0. So log of phi goes to infinity when one goes to z0. So this harmonic function u, which is defined in the interior of this domain U, has a pole at z0. In the neighborhood of z0, u of z has the form, is equivalent to log of, how is it? Okay, because again, I'm assuming that the function phi exists, and I try to construct it. So close to the point z0, phi has the form log of z minus z0. Okay? So now this gives the following definition. Definition. So we are given some domain U in C, which is simply connected. We are given a point in U, and we define a green function. By definition, a green function associated to u in z0 is a function u from u minus z0 to r, which is harmonic, which is 0 on the boundary, and which in the neighborhood of z0 has this behavior. And u of z minus log of z minus z0 is a harmonic function, let's say v of z, where v is harmonic and smooth and defined everywhere and defined in the neighborhood of z0. Where v is the harmonic function defined in the neighborhood of 0. So a green function, by definition, is a function that we, in the back of our mind, we think will be the real part of the log of the function we are looking at. But we copy what we discovered of u for the green function. Green function is a function which is harmonic in the complement of z0, which on the boundary is 0, and which in the neighborhood of z0 is not very complicated. It's a log plus a smooth harmonic function. And the claim is that there is such a green function. Claim is there is a green function. And that's very easy. Well, you take the function, let's say w of z is equal to log of z minus z0. This is a function which is defined in the complement of z0. You forget it, you just restrict it to the boundary. This is a genuine function, a regular function on the boundary of u with real values. You use theorem A. This function w can be extended to a harmonic function. So you choose some harmonic function. Let me call it w bar is a harmonic function which is defined on the full of u without exception and which extends w. Now what you do is you take, you define u of z to be equal to w bar of z minus or plus, I don't know, w of z. Am I right? Yes. Look, I claim this is a green function. Why? Away from z0, it's the difference of two harmonic functions. So it's harmonic. On the boundary, it is 0. Because on the boundary, w bar and w agree. And in the neighborhood of Z0, my function u precisely is the sum of a log and a harmonic function. So maybe there's a mistake with the sign. No, it's good. Maybe it was this one, no? Yes. No. No, I think it's okay. In the neighborhood of Z0, my function u okay, sorry. Minus here. Okay, take this function, harmonic function, away from Z0, restrict it to the boundary, extend it harmonically. Define the function u as w bar minus w. This function u is defined everywhere except Z0. Away from Z0 is the difference of two harmonic functions, therefore it's harmonic. On the boundary, it is the difference between w bar and w which agree on the boundary, so it's 0. And close to Z0, this function u is indeed a regular harmonic function plus log of z minus z0. So it's a green function. Okay? So it follows that theorem A does imply that there is a green function. And now I can prove the existence of this function phi, but it's very easy by this. We know u of z. This is known, and we want to reconstruct the function phi. Well, that's very easy. U of z is harmonic. Hence, locally, u of z is the real part of some holomorphic function. This holomorphic function, I know what it is. It will be log phi z. So I define phi of z, by definition, to be the exponential of f of z. So you may complain that the function f of z is not really well defined because I said a harmonic function is locally the real part of a function. A holomorphic function is 2. So to make it this function f global, I would need a simply connected domain. But the punctured domain u minus z0 is not simply connected. So this means that this holomorphic function f is not globally defined on u. When you go around the puncture z0, you have an ambiguity of 2i pi. So this function f of z is not well defined. It's defined up to a multiple of 2i pi. But this ambiguity of 2i pi is destroyed when I take the exponential. So even though f of z is not well defined, its exponential is well defined. And indeed, this gives a holomorphic function phi from the domain to the disk, which satisfies theorem A. Is it? Yeah. Okay, so again, I think it may be time to stop now. Let me just give a summary of where we are. Riemann had this brilliant idea that given a simply connected domain, you can minimize the energy, and this minimum will give you an extension by harmonic function. This is a brilliant idea. Unfortunately, it was 100 years earlier the possibility of having an actual proof. Nevertheless, he went on, and assuming the existence of this harmonic extension, he could prove the conformal representation of any simply connected domain on the disk. This is correct. This has not been changed since then. The existence of Dirichlet extension guarantees almost immediately the existence of this conformal representation. This is correct. Then there was this complaint by Weierstrass that there was no reason to believe that a functional in infinite dimension has a minimum. He gave this counterexample, very easy counterexample. Fortunately, Riemann was not aware of that. And the only, between 1870 and 1900, the only option not to use the wrong argument of Riemann was the proposed solution by Schwarz. Schwarz began by looking at the simplest example he could have in mind, triangle. I will discuss that tomorrow. Take a triangle. He will construct explicitly the representation to the disk. For polygons, he was not able to do it. I will explain why. But he was clever enough to create a method which enables you, given two domains that you know how to map to the disk, to map the union of the two to the disk. So he could go to polygons, and going to some limit procedure, he could go to any simply connected domain. So indeed, Schwarz had a complete proof by 1870 or something, which turned out to be interesting by itself, because you will see tomorrow, I think, you will see that the solution of Schwarz of finding mappings from polygons to the disk led him immediately to solving differential equations in the complex domain. And that's the first time uniformization will be linked with another fascinating subject, which is the study of differential equations in the complex domain. That will be the real motivation for Poincaré, when Poincaré will try to understand hypergeometric equations and more generally linear differential equations with algebraic coefficients. Really, Poincaré was interested by differential equations. He was not interested by that. He was interested by differential equations, and soon he will understand that Schwarz was ahead of him, and Schwarz was showing him the right direction. So it was good that the proof of Riemann was wrong, because it gave the opportunity to Schwarz to find some link between this subject and differential equations. If Hilbert had found the proof immediately the day after Riemann, this link would have been lost. Okay, thank you very much. So tomorrow we go to Hermann Schwarz with no T.